We said earlier that the Runqueue is only logically a queue. It could also be represented as multiple queues, like when dealing with different priorities, or it could be a tree, or some other type of data structure. Regardless of the data structure, what is important is that it should be easy for the scheduler to find the next thread to run given the scheduling criteria. If we want the I/O and CPU-bound tasks in the system to have different time slice values, we have two options. The first option is to maintain a single Runqueue structure, but to make it easy for the scheduler to figure out what type of task is being scheduled so that it can apply the different policy. Another option is to completely separate I/O and CPU-bound tasks into two different data structures, two different Runqueues, and then with each Runqueue associate a different kind of policy that's suitable for CPU versus for I/O-bound tasks. One solution for this is this type of data structure that we'll explain now. It is a multi-queue data structure that internally it has multiple separate queues. Let's say in the first Runqueue, we'll place the most I/O-intensive tasks, and we will assign with this Runqueue a time slice of 8 milliseconds. Let's say for the tasks that are of medium I/O intensity, so they have a mix of I/O and CPU processing, we have a separate queue in this multi-queue data structure, and here we assign with this queue a time slice of 16 milliseconds. And then for all of our CPU-intensive tasks, we'll use another queue in the multi-queue data structure, and here we'll associate with these a time slice basically that's infinite. So this will be like the first come, first serve policy. From the scheduler's perspective, the I/O-intensive tasks have the highest priority, which means that the scheduler will always check on this queue first, the queue that's associated with the I/O-intensive tasks. And the CPU-bound tasks will be treated as tasks with lowest priority. So this queue will be the last one to be checked when trying to figure out what is the next task to be scheduled. So depending on the type of task that we have, we place it in the appropriate queue, and on the other side, the scheduler selects which task to run next based on highest priority, medium, and then lowest. So in this way, we both provide the time slicing benefits for those tasks that benefit for the I/O-bound tasks and avoid the time slicing overheads for the CPU-bound tasks. But how do we know if a task is CPU or I/O intensive? How do we know how I/O intensive is a task? Now, we can use for that some history-based heuristics, like let this task run and then decide what to do with it, sort of like what we explained with the shortest job first algorithm. But what about new tasks? Or what about tasks that have dynamic changes in their behavior? To deal with those problems, we will treat these three queues not as three separate Runqueues, but as one single multi-queue data structure. This is how this data structure will be used. When a task first enters the system, so a newly created task, we'll enter it in the topmost queue, the one that has the lowest time slice associated with it. It's like we're expecting that it's the most demanding task when it comes to the scheduling operations, that it will need to be context switched most often. If the task stops executing before these 8 milliseconds, so whether it heals voluntarily or it stops because it needs to wait on an I/O operation, that means we made a good choice. The task is indeed fairly I/O interactive, and so we want to keep the task in this level. So next time around, when it becomes runnable after that I/O operation completes, it will be placed in this exact same queue. However, if the task ends up using up its entire time slice, that means that it was actually more CPU intensive than we originally thought. So we will push it down the next level. It will be preempted from over here, but then the next time it needs to run, it will actually be pushed into this queue. So it will be scheduled from this queue. If the task ends up getting preempted when it was scheduled from this queue, so it used up its entire 60 millisecond time slice, that means that it's even more CPU intensive. So in that case, it will even get pushed down to the bottom queue. So we basically have a mechanism to push the task down these levels based on its historic information. Although we didn't know if a task is I/O or CPU intensive to start with, we made an assumption and then we were able to correct for it. So we assumed that it's I/O intensive and we were able to correct and push it down these levels, down to the lowest most level in case it's CPU intensive. Now, if a task that's in one of the lower queues all of a sudden starts getting repeatedly releasing the CPU earlier than whatever the time slice specifies because it is waiting on IO operation, that will be a hint to the scheduler to say, oh, well, this task is more IO intensive than I originally thought, and it can push it up at one of the queues that are on the higher levels. This resulting data structure is called a multi-level feedback queue. And for the design of this data structure, along with other work on time-sharing system, Fernando Corbata received the Turing Award, which is like the highest award in computer science. It's the equivalent of the Nobel Prize for computing. I want to make sure you don't trivialize the contribution of this data structure and say that it's equivalent to priority queues. First of all, there are different scheduling policies that are associated with each of the different levels that are part of this data structure. More uniquely, however, this data structure incorporates this feedback mechanism that allows us over time to adjust which one of these levels will we place a task in when we're trying to figure out what is the best time-sharing schedule for the mix of tasks in a system. The Linux so-called O of 1 scheduler that we will talk about next uses some of the mechanisms borrowed from this data structure as well. And we won't describe the Solaris scheduling mechanism, but I just want to mention that that's pretty much a multi-level feedback queue with 60 levels, so 60 sub-queues, and also some fancy feedback rules that determine how and when a thread gets pushed up and down these different levels.